Okay. So we had ended up with the statements of the first two laws, the law of inertia and the second law, which was the force law. Today we will complete the discussion about the three laws with the third law, and then mainly look into applications of Newton's second law. Let's take a quick recap of the second law that we had seen. So the statement of the second law was that the net external force acting on a body equals to the rate of change of its momentum. Okay. But we also understood in this statement that this implies that the net force becomes mass into acceleration when the mass of the body is fixed. And that is what we look at most of the times, other than special systems which have variable mass, which will come in a later chapter. So in this chapter, we will always look at rigid bodies or bodies which have fixed mass. So for us, the working definition of Newton's second law will become this one, that net force is equal to mass into acceleration. So let's look at an example. Yes. So if we have a block like this, which is under the action of gravity, but such that we are applying two forces on it, like this, F1 and F2. Now these forces are applied such that they are symmetrically at an angle of 30 degrees to the vertical like this. So a block of mass, say 20 kilograms, take the value of g as 10 meters per second square, is vertically suspended in equilibrium under the action of two forces, F1 and F2, that balance its weight. Okay. Calculate magnitudes of F1 and F2 in newtons. Okay. So let's begin today's session with the discussion of this question. Just make a note of it quickly first. Alright, so let's begin by understanding what we mean by the term equilibrium. So equilibrium का मतलब क्या है यहाँ पे? Equilibrium means that the body will be at rest with net force zero. So the term equilibrium is defined as the condition for net force equal to zero. Okay. So in this above case, there are three forces which are acting on the body actually. Though in the diagram earlier we had shown two forces, F1 and F2, but naturally there's the weight of the body also. So this is like the third force. So in this case, and it is in equilibrium. Because it is in equilibrium, it means that the net force acting on it, which is the vector sum of these three forces, this should be equal to 0. Okay, where F3 is the weight of the body, which is mg vertically downwards, and F1 and F2 are forces applied by some external agent, and they are in a direction which we have shown earlier, that this angle is equal to this angle, which is 30 degrees. Okay. So basically we have to solve for this condition now, that F1 plus F2 plus F3 should be equal to 0. So it becomes a problem of vector algebra. Okay, so just work it out using vectors. Okay, nobody got the answer yet. It's pretty easy question actually. You have to just make the vector sum of the three forces equal to 0. So what you can do is you can use component algebra. That's one easy thing to do. The three forces that are acting are like this. So you can take your x and y axis like this. And then so because this angle is 30 degrees or this angle is 60, you can divide this into components. Same way you can divide this into components also. So F1, when you divide it into components, this one will become F1 by 2 and this will become F1 root 3 by 2. Similarly, when you divide F2 into components, again this angle is 30 or this angle is 60. So this is F2 by 2. This is F2 root 3 by 2. Okay. So the condition for the net force to be 0 is that along x-axis F1 by 2 minus F2 by 2 should be 0. They should cancel each other. So F1's magnitude should be equal to F2's magnitude. This is the first thing we understand. And along y-axis, again F1 root 3 by 2 plus F2 root 3 by 2, but minus mg because this is acting along the negative y-axis. This should be 0. So this is our second equation. Okay. So now what you do is you substitute the condition from the first equation here. So this becomes F1 root 3 by 2 plus F1 root 3 by 2 because F2 is equal to F1, that's equal to mg. So F1 root 3 is equal to, now m was 20 kg and g was 10. So F1 is equal to 200 by root 3 newtons. So ultimately we understand that F1's magnitude is equal to F2's magnitude, which is equal to 200 by root 3 newtons. So this becomes our final answer over there. Okay, so just make a note of this, people. So this is a very standard type of question as far as Newton's laws is concerned. Right. So hope this is clear, people. Okay. Now we will move on to understanding Newton's third law of motion before we come back to applications again of second law. We'll complete the theory part first. So Newton's third law, as you know, it's called the action-reaction principle. So the simple statement is that every action has an equal and opposite reaction. So this is, sure all of you have experienced the painful truth about this law. Okay, that if you use any part of your anatomy, like your hand or foot or something, to hit something or inflict a force on something or inflict pain on something, it experiences an equal and opposite force, and as a result, it can be a painful experience for you. So if you tend to hit an object very hard with your hand also experiences a sharp pain in response to the reaction force. Okay. So let us understand this in slightly more technical language. So what it means is that if a body, let's say A, applies a force F on another body, let's say B, then B will apply an equal and opposite force. So in vector language, you will write that as minus of F because the direction is opposite but the magnitude is the same on E. Okay. So this force F now acts like, let's say, the action. So what B is applying on A, that becomes the reaction. Okay. Now, very basic example of this is, for example, electrostatic attraction between positive and negative charge. This is something that shows this property about force. If we have a body A which is positively charged, a body B which is negatively charged, okay, this will experience a force like this. This will experience a force like this. So let us say we label this as force on B because of A. This is force on A because of B. So force on B because of A will be minus of force on A because of B. In other words, they are equal in magnitude but opposite in direction. So one of the very fundamental forces at the particle level known in physics, which is electrostatic attraction, it displays this particular property, as do all forces without exception. Okay, so there are many such examples of action reaction pairs, and we can understand a few more. Like, for example, if we have a situation like this, that there is a spring attached to a wall, and now next what we do is we stretch the spring out by applying some force to it. Okay. So what we are doing is we are pulling the spring with some force like this, but the spring will also apply a reaction force. So F is the force which we can call the action applied by the person to stretch the spring. In this case, you can see R is the reaction force, simply called the reaction, applied by the spring on the person. Another example of action reaction pair is when you keep an object on a horizontal surface, like on a tabletop or on the floor or something. What happens is that because of the weight of the object pulling the object down, the object ends up applying a force on the table. And that force acts vertically downwards. Okay. But similarly, the block itself, because of the action of the floor below, experiences an equal and opposite force upwards. So this is the reaction force on the block by the surface. Okay. So if this is the action, this is the reaction. So many such more examples we will keep studying as we move along. Okay. So all forces known in physics, they always act in action reaction pairs. Okay, so hope you've understood this. Moving on to the next concept in Newton's laws of motion. So we will see some common forces in what we call mechanical systems. So the most fundamental one here is weight, which we all know. This is the gravitational force acting on a body or object or particle of mass m on the Earth's surface. So that weight is equal to mg and always acts vertically downwards. So whether the object is at rest on a surface or the object is sliding down an inclined plane or the object may even be in free fall, then acceleration equal to g. Whatever be the case, its weight will always be a vector which acts in the direction which is vertically downwards and has a magnitude of mass into acceleration due to gravity. So in all these cases, so in this case its acceleration is zero. In this case, it has some kind of an acceleration down the incline. In this case, it has an acceleration which is equal to g because it's in free fall. But as far as the weight is concerned, that is not affected. That is not a force affected by the situation of the block. Whether it is in the first situation, second or third or any other situation, the weight will always invariably it will be a force which is vertically downwards and of magnitude mg. Where you know the value of g is, I mean, first of all, g is called acceleration due to gravity. Okay. At the Earth's surface, and it has a value of 9.8 meters per second square, or sometimes you approximate it as 10 meters per second square. So make a note of this also, please. Okay, so this is the first of the fundamental type of forces or the common type of forces. The next up, we will see a force called normal reaction force. Now, this is something little different to weight. We generally denote this with the symbol N. Problems we use the symbol N to denote it. So, normal reaction force, this is the contact force that acts between a body and a surface, or two bodies in contact in the direction perpendicular to the plane of contact. Okay. So very similar to the example we had seen earlier for the action reaction principle, when I had explained to you how a body lying on a horizontal surface applies a downward force on it, and the surface applies an equal and opposite upward force on it. So that type of force, that is basically a contact force that acts when an object is in contact with the surface. So that type of contact force is given a specific name, and that name is normal reaction. So here, this N is the normal reaction force applied on that block by the surface it is lying on. Now, similarly, if we look at an example where the object is lying on a inclined surface instead of a horizontal surface, we have an object like a block, okay, or it could even be an object like a cylinder or a sphere or whatever. They'll always experience a normal contact force which will be in the direction perpendicular to the surface. So in this case, it becomes along this sort of direction. This will experience a force along this sort of direction. Be along this line, which is perpendicular to this. Force will be along this line, which is perpendicular to the surface. So make a note of this, please. Okay, so next up, let's look at some numerical examples of the calculation of normal reaction force. So the first one is the most basic type of example, that if we have just a very simple situation of a block lying on a horizontal surface. So a block of mass, suppose 5 kilograms, lies on a horizontal surface. Yeah, Gazanfer, if an object is in free fall, na, it is not in contact with any surface, so there is no normal reaction acting on it. So not just when an object is in free fall, but suppose we have a situation like this, instead of the block being on the floor, you suspended it using a thread. So in this case, there is no normal reaction acting on the block, okay, because the block is not in contact with any surface. It has to be in contact with something, with some surface. So the condition for normal reaction to act on it is that it has to be in contact with another body or another surface. So yeah, free fall also includes that case. Okay, so now in this case, we want to calculate the magnitude of the normal reaction force on the body and take G as 10 meters per second square. So when we sit down to calculate it, what we'll understand is that on the body there are two forces acting. One is the surface below is applying this sort of normal reaction force on it. The surface below is pushing it up with this normal reaction force. Whereas the Earth's gravity is applying the force of weight on it vertically downwards. The object is also tending to get pulled downwards because of the weight. But the object has zero acceleration. It is at rest. Okay. So therefore, since the block is at rest, that means you should apply equilibrium condition. It implies that mg and normal reaction balance each other, so that the net force becomes zero. So they are equal and opposite forces, which means the magnitude of the normal reaction should be equal to how much? It should be equal to the magnitude of the weight. In this case, the magnitude of the normal reaction should become 50 newtons. Okay, so make a note of this example, please. Okay, so let's look at another situation. Now, next example. Suppose we have again a horizontal surface with a block on top of it, but this time there is another block stacked on top of this one. So we have this kind of situation. So you can see that there are two surfaces of contact. One is between the block A and the block B, there is a surface of contact, and then there is also between the block B and the ground. Okay. So A and B are two blocks of masses, let us say 2 kilograms and 3 kilograms. Find the normal reaction force between A and B, and secondly between B and the ground or the horizontal surface. Okay. Assume the system is in equilibrium. Okay. At rest, in fact, and G is equal to 10 meters per second. Just try this out, people. We will discuss. Nobody's got the answers yet. Okay, see, what you have to do here is you have to understand that on the block A, there will be two forces which are acting. One is that the block B from below will be pushing up with some normal reaction force. So let us say this is N1. So this is the force of normal reaction between A and B. And of course, there will be the weight of the object. That is mass of A into G. And the block is at rest. So N1 should balance the weight of this. So this becomes our first equation. So N1 becomes 20 newtons. Because the mass of A we have taken as 2 kgs. Okay. Now similarly, when you turn your attention to the block B, so you realize that on the block B, this time there are three forces which are acting, not two. Why three forces? Because there is something on top of it, that is the block A, and that will apply a contact force on it downwards. So there will be a normal reaction applied by A on it vertically downwards. Because A is on top of it. So this N1 and this N1 are an action reaction pair. But similarly, there will also be a contact force applied by the floor on B. This is N2. And of course, there is B's own weight, which the earth is applying on B. And B is also in equilibrium. So for B, what is happening? N2 plus the weight are together balanced by N1. This is the second equation. Sorry, N1 plus the weight are together balanced by N1. The two downward forces, which are N1 and the weight, are balanced by the one upward force, which is N2. So from this, we'll get N2 as N1, which was 20 newtons, plus mg for B, which is 30 newtons. So N2 will work out to be 50 newtons. So this becomes the full solution of this question. Excuse me. Okay, so hope this question is clear. Now, before we proceed with more examples of how to calculate normal reaction forces and related questions, we will discuss a general method of solving Newton's law problems, which is called the free body diagram method. So this is a specific method with certain steps that we apply to make the solving part of Newton's laws of, particularly Newton's second law, more easy, where we have to solve for the equation that net force is equal to mass into acceleration. In the above few examples that we saw, the net force was zero because the body was in equilibrium. So whether that is the case or whether the acceleration is non-zero, in both cases, we always have to solve for the net force on the left-hand side of Newton's second law by doing the vector sum of all the forces. So for doing that vector sum of all the forces, there is a specific you know method that we apply which involves specific steps, and that method is called the free body diagram method. So this is something very important and which is something very universal that we'll apply not only in this Newton's laws chapter but generally in mechanics. The understanding the free body diagram of an object and thereby being able to understand the forces acting on it becomes very important. So let us discuss about this in detail next. So in short we call it FBD, and free body diagram analysis for a given body or object. So the free body diagram is nothing but a simple geometrical representation of a body and the forces acting on it. In this, the body itself is shown as a point mass or particle, and all external forces acting on it are drawn as vector arrows originating from that particle. Okay. So just note down this definition of free body diagram first, then we'll see some examples. Okay, so let's see some quick examples of free body diagrams. So, for example, we start with one of the cases we have just seen of those two blocks kept stacked on top of each other. The example that we just saw previously, this one. So, in this example, the free body diagram for the block E, okay, that one will look like this. We represent the block by a point mass, and on that point mass, we will show the two forces acting on it. One was a normal reaction applied by the block B on it, and the other was the weight of it, which was acting downwards. Okay. There's also another object in the diagram. So let's make that one's free body diagram. So again, we will show it as a point mass, but there will be three forces acting on that point mass. There will be normal reaction applied by the ground. There will be its own weight. But in addition to this, there will also be another force, which is a normal reaction that A is applying on B. That will be like this. So this is how the two free body diagrams would look in this particular case. So make a note of this one. Okay. Next up, let's look at another example. So we have this situation. This is a cylinder of mass m, and this is a smooth inclined plane. So make the free body diagram for the cylinder, okay, and show the angle of normal reaction force with respect to the horizontal and the vertical. So we'll understand here that the normal reaction will act along this sort of axis because it has to act normal to the inclined plane. It has to act along this kind of line. Okay. So when we make the free body diagram, remember we will represent the body by just a particle or a point mass. But on that there will be two forces acting. One will be normal reaction, the other will be weight. Now weight is the force that will act down the inclined plane. Sorry, weight is the force that will act vertically downwards, whereas normal reaction is the force that will act along this direction, which is the normal to the inclined plane. This is the inclined plane axis. So let's take in our example, suppose theta is equal to 30 degrees. Okay. So here, because this angle is 90, what we'll understand that if we draw a vertical over here, draw a vertical line over here, this angle is 60 degrees, which means that this angle is 30 degrees. Okay. So that is what becomes important in the free body diagram. Okay. So in the free body diagram, N is the normal reaction contact force on the block applied by the surface. Mg is of course weight. Okay. But more importantly, if we draw the vertical axis here and the horizontal axis here, like this, okay, we can see that with respect to the floor, this angle was theta equal to 30 degrees. So this angle is 30 degrees. So that now means that this angle here is 60 degrees. Okay. And this angle is 30 degrees. Yes, of course, this is a 90-degree angle. So the normal reaction is at 60 degrees with respect to horizontal, or that is the same thing as 30 degrees with respect to the vertical. Okay, people. So hope you've understood the angles involved in this particular case. Okay. So with this, we complete today's session. So please go through the section about free body diagram and normal reaction force from your modules or from your CET. I mean, from your HSC textbook, Newton's laws, or from your module for CET, which is the IIT and sub module. And we will discuss some more questions and things next time. You can also start doing the exercise from the module. So from the first exercise in your CET module, you can work out the first 10 questions of Newton's laws of motion. Okay. So that's it for today's class, people. All the best and thanks.